Hello students, welcome to Think, Understand and Bloom with Rashida. Today we are going to discuss a graphical method with the maximization problem. Here is our question that we have to solve a LPP problem with a method of a graphical. The question is given here, maximum z is equals to 40x1 plus 50x2 subject to the constraints x1 plus 2x2 less than or is equals to 40, 4x1 plus 3x2 less than or is equals to 120, whereas x1 and x2 greater than or is equals to 0. Let's move to the step 1. Let's convert the given inequalities into the equations. So our first step will be, these are our constraints that has given. We have converted into the equations. X1 plus 2x2 is equals to 40. We will consider this equation as a equation 1, and 4x1 plus 3x2 is equals to 120. That is a equation 2. We will find the values for the variables x1 and x2 by placing x1 is equals to 0, and we'll find the x2, and then we'll keep x2 is equals to 0 to find the x1 value, to find the coordinates to draw the graph. This is our equation 1. We are writing here equation 1, x1 plus 2x2 is equals to 40. We will put x1 is equals to 0 in equation 1, replacing here 0 plus 2 into x2 is equals to 40. It will become 2x2 is equals to 40, x2 is equals to 40 divided by 2, 20. x2 is equals to 20. Here we will write x1 and x2 0, 20, whereas x1 is equals to 0 and x2 become 20. x2 is equals to 0 in the same equation 1. x1 plus 2 into 0 is equals to 40. It will become x1 is equals to 40. x1 is equals to 40 and x2 is a 0. Firstly, we placed a x1 is equals to 0 in the equation. We got a 20. 0, 20. And again in the same equation, we placed x2 is equals to 0. x2 is equals to 0 and we got a x1 is equals to, we'll write a equation 2 is 4x1 plus 3x2 is equals to 120. Same. Again, we'll put x1 is equals to 0 in equation 2. It will become 4 into 0 plus 3x2 is equals to 120. It will become 3x2 is equals to 120. x2 is equals to 120 divided by 40. Next, we'll put x2 is equals to, in the same, become x1 plus 3 into 0 is equals to 120. For x1 become here x1 is equals to 0, then we got a 40. When x2 is equals to 0, we got a 30. Using these two equations as a x1 and x2 line, will draw a graph by using these coordinates. This is our graph. On x-axis, I took a x1 variable, and on y-axis, I took a x2 as a variable. On x-axis, 1 unit is equals to 10 centimeters, and on y-axis, 1 unit is equals to 10 centimeters. Why? 1 unit is equals to the 10 centimeters here. So we got our coordinates. We are having x1 and x2, x1 and x2, whereas x1 is equals to 0 and x2 is a 20. Means on the line 20, we'll point it as a 2 is a 20, and on the other side x1 is equals to 0 and 0, 20 and 140, x2 0. x1 is equals to 0, x2 is equals to 20 and x1 is equals to 40 and x2 is a 0. This is our first equation line. Join these 2 points. In the same way, the equation 2, we are having 0, 40 and 30, 0. Graph 0, 40 will point here at 40, and next 30, 0 will join these 2 points. The intersection point we can see here at this is 25, 30 here at 24, and on the y-axis, that is on x2 line, that is 8, 24, 8. We got a intersection point here. This closed boundary forms a feasible region. O. A feasible region is the area on the graph that contains all feasible solutions. Here we are having A 0, 0, B 30, 0, and this is C, a point of intersection 24, 8. 24 on a x-axis and 8 on a y-axis, that is a x1 and x2 we have to, and another is a point D. Here is the D point, that is 0, 20. So this forms a feasible, to find a feasible solution. Any solution that lies inside or on the boundary of a feasible region is called a feasible solution. In the maximization problem, we choose the corner point giving a highest z, and in the minimization we choose the corner giving the lowest z values, lowest z maximization z value. Graph, we found the A, B, C and D values which forms a feasible region, and to find the feasible solution we have to substitute all the values of a x1 and x2 to find the objective function and to find the optimal solution. Substitute the value of x1 and x2 into objective function and find the optimal solution. These are our coordinates A, B, C and D. We will substitute here in the objective function maximum z, that is 40 into 0 plus 50 into 0, and this is 40 into 30 plus 50 into 0. In the same way, 40 into, this is 24 plus 50 into 8, and here 40 into 0 plus 50 into 20. Z value we got at A 0, 0 is 0, at B point 30, 0 is a 1200, and at C 24, 8 is a 1360, and at D point, that is 0, 20, that is a 1000. So we can say that maximum Z value is a 1360 at C 24, 8. The maximum Z value is 1360 at a point C 24, 8. We can represent it as a x1, x2, that is a x1, x2 greater than or equals to 0 is a non-negative constraint. Let's move to the another problem of LPP, graphical method. Here we are using 3 constraints. Now let's convert the inequalities into equalities. That is our first step. So first constraint we'll consider as a equation 1, second constraint as a equation 2, and third constraint as a equation. In the next step, we are going to find the value for the variables of a x1 and x2 for all the 3 equations, and we'll find the 3 different coordinates so that we can find the feasible solution, and before that we have to find a feasible region by drawing the graph. These are step 2. Next, we'll find the coordinates by placing x1 is equals to 0 and then x2 is equals to 0. In the first equation, we'll put x1 is equals to 0. This will become 0 plus 4x2 is equals to 24. Here x2 will become 6. Here we will write x1 and x2. When x1 is equals to 0, x2 is a 6. Likewise, in the same way, we'll put x2 equals to 0 in the same equation. Then x1 and this will become 0 is equals to 24. When x2 is equals to 0, x1 is, we'll move to the next equation 2. If we keep x1 is equals to 0 in equation 2, this will become 0 plus x2 is equals to 21. When x1 is 0, x2 will become 21. In the same way, when x2 is equals to 0, this will become 3 into x1 plus 0 is equals to 21. In the same way, x1 is equals to 7. When x2 is equals to 0, x1 has become the same way in a third equation. If we put x1 is equals to 0, then x2 will become 9. When x2 is equals to 0 and x1 will become 9. This is x1 and x2. When x1 is 0, x2 is 9. When x2 is 0, x1 is 9. Using these coordinates of from equation 1, 2 and 3, we'll draw a graph. X-axis, I took a variable x1, and on a y-axis, I took a variable x2, and our 1 unit will be of a 2 centimeter, both on a x-axis and y-axis. X-axis is a x1 and on a y-axis is a x2. From equation 1, we are having our coordinates on x1 0, x2 is a 6 is the point here, and next on the x1, that is 24, x2 is a 0. We'll join these 2 points. The first equation, and from the second equation we are having 0 comma 21. This is 22 in the middle. Join these 2 points. Next, from equation 3, 0 comma 9 here, and here 9. We'll join these 2 points. This is our feasible region. Let's check the point. This is A, 0 comma 0, and this is B, 7 comma 0, and C point at 6 comma 3. 6 comma 3, and at D point, D we are having 4 and 5 on x-axis, and y-axis this is 4 comma 5, and E point, this is 0 comma 6. The coordinate points we got from the feasible region helps us to find the feasible solution. Point A 0 comma 0, B 7 comma 0, C 6 comma 3, D 4 comma 5, and E 0 comma 6. Substitute the coordinates in a maximize Z. This will become 2 into 0 plus 5 into 0. This will become 0, and 2 into 7 plus 5 into 0. This will become 14. 2 into 6 plus 5 into 3, 27. This will become 2 into 4 plus 2, 5. This will become 33. And this is 2 into 0 plus 5 into 6. This is 30. Highest optimum solution 33 at D 4 comma 5. Optimum value we got 33 at D 4 comma 5 means it's a feasible solution we got at a D 4 comma 5. Today we have discussed a graphical method of a LPP using a maximization method with a 2 constraints and as well as a 3 constraints. Next video we will discuss a minimization problem with a graphical method with the 2 constraints and a 3 constraints. See you in the next video. Thank you.